Okay, hi, I'm Ananya, and I'm basically going to talk about certain partial covering problems that we study in computer science and the kind of variants that are considered and the landscape of complexity, like in these for these problems. So, what are the kind of algorithms that are known? So, this talk is based on two works, which is joint work with Pallavi, Lochween, Fahad, Abhishek, Souvik, Saket, Tanmay, and Daniel. So, okay, so we'll start with what a CNF satisfiability formula is, a CNF Boolean formula. So, CNF stands for conjunctive normal form. So, any CNF formula consists of variables, let's say n variables, and for each variable, you can either have a positive literal xi or a negative literal, which is xi bar, and you have clauses. So, clauses are basically an OR of literals. So for example, this clause Cj is xa or xb or xc bar, so or of positive or negative literals. And a formula is an and of these clauses. So the goal in these problems is basically to come up with an assignment to the variables such that all the clauses in the formula is satisfiable. For example, for this particular formula, if you look at this clause can be satisfied if you either set the variable xa to 1, xb to 1, or xc to 0. And similarly, so you need to come up with assignment to all the n variables such that all the clauses are satisfied, right? And you say that a formula is satisfiable if there is a Boolean assignment to these variables such that all the clauses evaluate to true. And there's something called the weight of an assignment, which is basically the number of variables that you are setting to one or true. So we'll consider the MaxSat problem with cardinality constraint. So what I described earlier was the satisfiability problem, and in the MaxSat problem, you again have a CNF formula phi, and in addition, you also you have a positive integer k, and okay, so the point is that now you don't work with any assignment, but you need to come up with an assignment that sets at most k variables to 1 and satisfies as many clauses as possible. So you don't want to satisfy all the clauses here. So this problem is known to be NP complete, which means in polynomial time, it is unlikely to have an algorithm that solves this problem. And this problem is of great importance because it generalizes a lot of other problems as well. Uh, okay, and the second partial covering problem that we'll consider is the maximum coverage problem. So here you have a universe of n elements and a family of subsets over that is defined over this universe. So E1 to En are elements, and each Fi over here is a subset of these elements, and you're given an integer k, and the goal is to select k sets from F that covers as many elements as possible. So by covering, I mean the union of these k sets are the elements that are covered by these k sets. So this problem is also NP complete, and this problem is the monotone version of the CC MaxSat problem that we saw earlier. So basically, like if given any satisfiability formula, if you remove all the negated literals, then this can be reduced in polynomial time into a maximum coverage instance. So for example, here, the circles represent elements and the rectangles are sets. And let's say like all of these circles inside a rectangle are the elements that are a part of this rectangle. And for k is equal to 1, that is, you can only choose one set to cover as many elements as possible. So a natural greedy choice would be to select the rectangle that covers the maximum number of elements or maximum number of circles here. Okay, so what is known about these problems? So in polynomial time, there exists an approximation algorithm with factor 1 minus 1 by e. By this, I mean that there exists an algorithm that does not solve the problem exactly, but it comes up with k sets that covers some 1 minus 1 by e many elements, and this runs in polynomial time. That is, the running time of this algorithm is a polynomial function of the size of the input. So the question that naturally arises is that, okay, in polynomial time, can you come up with an algorithm that improves upon this factor? That is there an algorithm that covers more than 1 minus 1 by e number of elements? And the answer is no, unless some kind of an assumption is violated. It is not possible for polynomial time algorithm with a better factor. So the next question that you would like anybody would ask was, okay, what if we increase the amount of running time that is given to us? So these kind of algorithms are called FPT algorithms, where so n and m are basically the input. So n was the number of variables and m was the number of clauses in our input formula, and k is something called a parameter that we define. In the input, and now we want the running time to be polynomial in the input size, but the function on the parameter can be can be anything. It could be as bad as exponential or doubly exponential. So if we increase the running time, can we do better? So now we frame this problem as a parameterized problem. That is, the input is the same, but now along with the input, we have something called the parameter. So K here is the solution size, which is the number of sets that you want to pick to cover as many elements as possible. And the question remains the same. But now the running time goal changes. So instead of just having a running time that is just polynomial in the input size, you want a polynomial of this kind. You want a running time of this kind. Okay, so the answer to this question is again no. That is, even if you assign this kind of a running time, if you're given this kind of a budget of running time, even then you cannot solve this problem exactly. So that's what it means by saying W too hard. And so it seems natural to combine both these problems, FPT as well as approximation. And the next question that we can ask is, okay, so we have this kind of a running time budget with us, where the running time is some function of k and epsilon. Epsilon is another input parameter, and you have some polynomial in the input size. And now instead of asking if we can solve this problem exactly, can we come up with an approximation factor which is better than the approximation factor that you can achieve in polynomial time? So before we go there, so the first result that we got was, okay, these two problems are actually equivalent in terms of FPT approximation. So FPT approximation is like the realm where you try to come up with approximate solutions, but in FPT kind of running times. So this is sort of more powerful than polynomial time or approximation or just FPT itself. So, so like the first thing was, okay, these two problems are equivalent, which is kind of a surprise, because we just said that maximum coverage is a monotone version of CC maxsat. That is, if you remove all the negative literals, then any input instance of CC maxsat can be reduced to a maximum coverage instance. What this means is that, okay, the first problem is at least as hard as maximum coverage. But when you consider the realm of FPT approximation, these two problems are essentially like equivalent. So there is basically a polynomial time reduction, which is a randomized reduction that takes an instance of CC maxsat and converts it into an instance of maximum coverage with this success probability, some big O epsilon to the power k. Okay, so so this is the randomized reduction. So you first come up with a random assignment to the variables, where for each variable x, you either set it to 0 with probability 1 minus p or 1 with probability p. And then you remove, so from the, so you construct a new formula as follows. You remove all the clauses that are negatively satisfied. That is, if there is a clause that has a negative literal, and that is set to 0 by the random assignment that you constructed, then you remove those kind of clauses. and you also remove all clauses that appear as a negative literal. So in essence, you get a formula which has only positive literals. So now we can convert this resulting formula into an instance of maximum coverage by a procedure. Okay, so so that is the kind of equivalence that we saw, and now these kind of problems. So there are like multiple variants of these problems that can be studied. So the first is, okay, if we implement fairness constraints on these problems, that is, so we define something called the fair maximum coverage, where okay, given a set system u comma f, the input is the same as maximum coverage, where you're given a set system u comma f and a positive integer k, but now you add colors to the elements of u. That is, so every element of u gets one of the colors from 1 to r. So r is the number of colors, and for each color you have a coverage requirement as well. So now you need to find k sets from f that cover at least ti elements of color I. So similarly, you have something called the fair max sat, where in addition to the CNF formula phi and a positive integer k, you now have colors on the set of clauses and a coverage requirement for each color. And you want to find an assignment that sets at most k variables to 1. And this particular assignment should satisfy at least ti clauses of each color. Okay. So the second constraint is the matroid constraint. So before that, we'll look at what matroids are. So matroid is again a pair where pair u comma I, where u is a ground set and I is a family of subsets over u, and it's it satisfies certain axioms. So the empty set should belong to the set I, and if there is a set A in I, then all of its subsets should also belong to I. And then for any two subsets A and B, where B has size strictly greater than A, there should, then there exists an element E which is in B but not in A. And if you look at the set A union E, then this particular set should also belong to the set I. Now the elements of the set I are called independent sets, and the maximum size of any independent set is called the rank of a matroid. Okay, so in the matroid constraint version of this problem, we consider, okay, we have the set system u comma f, and now we have a matroid on the sets f. And this matroid is of rank k, that is the size of any independent set, maximum size of any independent set is k. And now you want to find a subfamily f of size k, like any subfamily f hat, such that this, so saying that this f hat should belong to I means that, okay, this the size of this subfamily that you're finding cannot exceed k because of this matroid constraint, and you want to maximize the number of elements that you can cover using this subfamily. So similarly, you can define the max sat. So now you're trying to find a weight k assignment such that if you look at the set of variables that are assigned 1, this set of variables must be an independent set in M. So now the matroid constraint in this particular formula is on the set of variables. Okay, so the randomized reduction that we discussed earlier, it has certain features. So this particular reduction can accommodate the fairness and matroid constraints. That is, if we are given a CC maxad instance, which has the fairness constraint embedded into it, then the resulting max coverage instance is also fair. And this also holds true for the matroid constraints. And if the variable clause incidence graph of the formula belongs to some kind of a family H, then for the input formula, that is the input instance of the CC max sat, then the resulting instance of max coverage will also satisfy the same. So by this, I mean, okay, if the variable clause incidence graph is again like a bipartite graph, where one partition contains a vertex for the variables and the other partition contains a vertex for the clauses, and there is an edge between a variable vertex and a clause vertex if the variable belongs to the clause. So, so if this particular bipartite graph has some kind of a structure, for example, if this is, let's say, every element in, so every vertex in this particular partition has degree at most D, then if you look at the incidence graph of the maximum coverage instance, then the same property holds as well. Yeah, so now we revisit this question, that is like, given FPT amount of time, can we come up with an algorithm that solves this problem approximately? And unfortunately, the answer to this is also no. That is, even if there are K sets that cover the entire universe, uh, even then, assuming some complexity theory assumptions, there is no FPT time algorithm that can come up with an approximate solution for this problem. And these hardness constraints, hardness results also hold for CC MaxSat as well. Okay, so since the answer to this question is also no, we look at certain families of instances where these problems do admit the kind of algorithms that we talked about here. Okay, so so if you look at the bounded frequency instances, that is where every variable here has frequency at most D. That is, every element occurs in at most D sets. Then there is an FPT approximation scheme. So again, an FPT approximation scheme is where the algorithm takes FPT time and comes up with an approximate solution for the problem. So there is an FPT approximation scheme for these kind of instances, and also for KDD free instances. So a KDD is a bipartite graph where you have D variables on one side and D clauses on one side, and there is an edge between every pair of vertices across here. So this is a complete bipartite graph. And KDD free means okay, your clause variable incidence graph should not contain a KDD as a subgraph. So this essentially means that if you look at any subset of D variables, they cannot together occur in D clauses. Okay, and so KDD graphs encompass a lot of other kinds of graphs. So basically, they are a superclass of multiple other important graph classes that are considered. So any FPT approximation scheme on biclique free or KDD free graphs would also imply an FPT approximation in all these other graph classes as well. And so these are the results that we have for maximum coverage. So for any constraint, let's say for the Matroid constraint, and if you consider any incidence graph, whether this is KDD free or bounded frequency graphs, then we have a randomized algorithm which runs in FPT approximation time, and the parameter here is KD and epsilon. And similarly, we have deterministic algorithms for KDD free and randomized algorithms for bounded frequency case. And this takes an additional parameter, which is the set number of colors R. And if we consider both the constraints together, then we have randomized algorithms for both of these incidence graph classes, and with this kind of a running time. And for the CC MaxSat case, all the algorithms are randomized because of the randomized reduction. So given any CC MaxSat instance, we can use the randomized reduction that we discussed earlier. And it takes, so that reduction was basically a polytime reduction with success probability, some big O epsilon to the power k. So there is a trick called boosting, where if you repeat the algorithm some inverse of success probability times, then you can get a better algorithm with constant success probability. But since the success probability was of the form epsilon to the power k, so now the running time becomes some FPT in epsilon and k. So, and since it was a randomized reduction, these algorithms are also randomized. And these same algorithms that are mentioned here can be used once you use the randomized reduction to get a max coverage instance. So yeah, thank you.